Howdy folks, Mr. B again. We're going to do a really important topic today. We're going to look at balancing chemical reactions. Now this time I won't say that it's necessarily a short one because this is a topic that requires some serious explaining. So let's get to it. Okay. I really like this starting slide because what it does is it shows the combustion of a hydrocarbon. In this case, we're looking at methane. So I want to do some labeling here, right? We've got carbon and 4 hydrogens. There's one sneaking over here and there's one there. Okay. We've got oxygen here. And oxygen is one of those things, when we were looking at divalent elements, it's covalent. And what it's doing is it's sharing electrons and floating around as O2. When we bring methane and oxygen together, hashtag barbecue, right? You produce carbon dioxide waste and water. So what are we talking about? There's a rearranging that goes on. You get things with new properties. No longer do you have methane, the hydrocarbon. Right? You've got carbon dioxide. So here's your carbon. Now some of the oxygen is rearranged. We've got oxygen here. We've got 2 oxygens accounted for there. Where are the rest of the oxygens? Well, they're over here. Bam. And the hydrogens, depicted in white, there's 4. Now, when you look at this reaction, we had 1 methane molecule combined with 2 oxygen molecules, which produced 1 carbon dioxide molecule and 2 water molecules. If you do your accounting here, everything is here. And that's sometimes a little bit misleading in combustion reactions. People will see things combust. For example, if you burn a log in the fire, and you wonder where everything went. Well, there's a rule. You can't create nor destroy matter. Okay, it's the law of conservation of mass. It's a very famous principle. You can rearrange things. They might float away as a gas. Some of it might become ash, but it's all accounted for. Everything's there. Whether you can see it or not, it is. So what if we leave potassium metal, right, out in the air and just let it combine with oxygen? Well, over time, you'll start to get an oxide. This happens with silver too. Not exactly the same appearance, but silver, if you leave it out long enough, will get like a black film on it, and that's silver oxide. And you have to go get that white paste and you remove the oxide and you get back to the silver, but it'll still interact with oxygen gas. Some of the newest batteries they're talking about for electric vehicles are going to be potentially just working with oxygen, which is a cool idea. So, what do we have? Well, potassium metal and oxygen gas are what we call the reactants. Right? They show up to the dance and interact. What you get at the end is something you call a product. So what's the arrow for? It just means that when potassium metal and oxygen get together, sort of have a party, you yield potassium oxide, the product. You could say yields, or you can say produces. I'll leave it to you. Bam. So a skeleton equation accounts for where everything went chemically, right? Some things don't react, but some things do. A great number of things do. So let's figure out where everything went. First off, famous rule, it is K2O for a reason. We know that's the correct formula because you got 2 potassiums, right, with their oxidation state +1, and then you've got oxygen with an oxidation state 2-, and that is balanced. Boom. +2, -2, these are the proportions. So if that's the recipe, don't go changing the recipe. Don't go messing with this. What you can do is you could say how many showed up, right? And that very first slide, we were accounting for everything, but I was pointing out the number in front. And here's where polynomials are actually useful. Polynomials, when you're dealing with coefficients, however many x squared or xy's or whatever you have, I always call them counting numbers, or how many of the thing are you talking about? In this case, the thing is a molecule. Okay, so how many potassiums do we have to account for here? Well, if the formula is K2O as a product, you're going to see that, well, I don't seem to have the right amount of potassium. And then you take a look at oxygen. You say, well, there's only one oxygen there, whereas there's two there. Okay, since you're not allowed to change O2, right, what can you do? You can mess with the coefficients. So in order to balance this, I'm sort of looking at oxygen here. And I know that I'm going to need to do that. Why? Because that's like saying K2O twice. Right? So that's 4 of these and 2 of these for keeping track. I have made sure that there's 2 oxygen on each side, right? Because there's 2 here. So what do I have to do? Well, there's a lonely potassium over here, and if I just write the magic number 4 in front, we're balanced. Because we have 4 potassiums and we have 2 oxygens. And over here, 4 potassiums, 2 oxygens. Okay, so what we've done is we've written what's called a balanced equation from the skeleton. The skeleton doesn't have coefficients in it. We just take it from there. So yes, there are a great number of things that you have to do, you know, to balance these different equations, right? So what do we got? Well, first off, you go around counting atoms. And if you look at the subscript here, you know there's 2 bromines. So we'll put in a 2. We'll be using coefficients here. How many irons do we have? Well, if you're not sure, what you can do is you write FeBr3, FeBr3, and then you go counting. Say, well, there's 2 irons, and I see 3 bromines there, and I see 3 bromines there, for a grand total of 6. Bam, done. Now, there's a trick to this. You'll probably see. I'll do another one, writing this out, because it can get a bit long. But if we say do this, you can see this gets a little laborious, right? Well, now you can see it all. And on some assessments, I tell students, if you can't figure out the number of atoms, you could just write it out. It takes a little longer. But do a little accounting, and that is good for 12 potassiums total. And then our phosphates, do a different squiggly. We've got 4 phosphates. And then oxygen, 4, 8, 12, 16. Got it. There is a trick, and I'll show you in the 5th example how this trick works, but I do want you to start out just sort of basic and then just ease your way into this. Now, when we look at tin phosphate here, I didn't say what kind of tin, but I'm just being expedient. I know that we have 3 tins, so we'll go like that. Now I'm just going to write the phosphates beside, which is a little bit weird. You normally wouldn't write it this way, but I'm just doing this in a line. You see there's 4 phosphates and there's 16 oxygens. Is there an easier way? Yeah, there is. When you look at a coefficient, you can multiply the coefficient by the subscript. And when you do that, you see that there's going to be 9 tins, and there's going to be 3 nitrites. Now, not just 3 nitrites. Oops, got to get this over here. Haha. There were 4 to begin with, but you tripled the recipe. So let's just write this over here. It's like you have 12 of the nitrites. Okay, so you could probably see what effect this is going to have. You'll have 12 nitrogens, and there we go, 24 oxygens. And that accounts for quite a bit of stuff. Really does. So let's just zoom past that. So when you've got a skeletal equation, you have to forgive the GIF, and yes, I pronounce it GIF. We want to obey something called the law of conservation of mass. It's a law. You can't destroy matter. Now, when we talk about nuclear equations, that's going to be a little different because there is a relationship between matter and energy, and it has to go somewhere. A little bit like a Star Wars transporter. It gets kind of cool when we have those conversations. But the idea is that atoms can't be destroyed. Right? Sort of think back all the way to Dalton, right? And he talked about these impervious billiard balls, right? These atoms. And that's a bit of our atomic theory coming back, right? So atoms in the reactants, well, they have to be in the products. And the caveat is they've just been rearranged. Okay, so there's our potassium oxide above. And when we balance this, we did this previously, and we realized that's actually the recipe. 4 potassium atoms will interact with 1 oxygen molecule, and that's what produces your potassium oxide, right? Which dullens the appearance of potassium. Potassium's a metal, so it'll start to appear a little bit more dull, not as shiny. Okay, so what have we got going on? When you balance an equation, you have to count the number of atoms, right? You have to, on the reactant side and on the product side, right? And it's really important with diatomic elements. And the diatomic elements, right, you know them, like hydrogen, nitrogen, oxygen, fluorine. If we remember, the whole reason why chlorine floats around as Cl2 was because covalently it needed to satisfy its octet. So we write that as Cl2. And you realize, right, that happens with the halogens pretty much a lot of the time. We saw that nitrogen was a triple bonded molecule, oxygen is a double bonded molecule, satisfying the octet rule. Okay, so here is the list, right? Pretty cool. Now, when you do equation balancing, I remember doing this in high school when I first saw it, it can honestly be a little bit painful because there's a lot of trial and error and you're accounting for atoms on the reactant and product side. But I'm going to give you a tip, right? That polyatomic ions, balance them as a group, which is interesting because nobody told us to do that in high school. We were balancing, for example, we were balancing nitrate. We were never shown the polyatomic thing, so we were keeping track of the nitrogens and the oxygens separate. But since polyatomics, as long as they show up on the left and right-hand side, right, as long as they're in the reactants and they're in the products, they're a chunk. You can balance them as a chunk. Do it. Life is easier. So, what do we got? What we're talking about with the polyatomics is these right here. That's a chunk. There's a chunk there. And as long as you see, here's the nitrate on this side and here's the phosphate on this side, as long as you see that, you're golden. You can chase that around. Really kind of handy. So, when you go to balance it, only write in coefficients. Don't go changing the formula. It's tempting, don't do it. It'd be like if you dropped or spilled water on a laptop. You get the water off and the first thing you want to do is press the power button. It's the last thing you should do. If there's water in your laptop, I can tell you from experience, you might want to let that dry out and do your best. So, don't mess with the subscripts. Don't do it. It's tempting. So we'll go like this. Don't do it. Okay? Now, when it comes to balancing, you want to, there's a trick. If you balance your hydrogens last and your oxygens as the very last thing, you're going to find it a little bit easier. Now, that being said, it can be a little fun in combustion reactions, but we'll talk about that later. When you're done, you have to count the atoms. Sorry, it's accounting 101. Thou shalt do it. Okay. And speak of the devil, we forgot to balance above. Okay, so what do we have? Well, when you chase this one around, it can be a little bit ferocious, right? What do you really have to do, right? Now, just one sec. What you're going to have to do is account for your phosphates and your nitrites. There's a lot going on. So what do you have to do? Well, I'll show you the formula first. And you'll look at it and you'll say, holy moly, that's a lot of work. So 3 tin nitrites, and by the way, that's tin 4. Tin 4, good buddy. Sorry, bad joke. I couldn't resist it. 3 of the tin nitrites, 4 molecules of potassium phosphate produce 12 molecules of potassium nitrite and 1 molecule of tin. Now it's the same kind of tin, right? So tin 4 phosphate. Like, holy moly, that's a lot to track. So this is balanced, but let's start out with a couple of easier examples, okay? So we're going to chase this around. Let's see what we got. Now, what I've got at the bottom is a little sort of table, right? And we'll fill this in as we do it. When we go after any element we want, we could say, well, let's go after sodium, okay? Sodium, well, sodium's one thing to go after. Actually, if you look at it, there's a lot of things you could go after, right? What if, I'm actually going to back up. I'm going to go after aluminum. Why? Here's what caught my eye. I was going to go after sodium, but I like this a bit better. There's 2 aluminums accounted for on the product side, so I'm going to go over and do this. Okay, so as far as our aluminum go, we've got a 2 to 2 ratio on the product side and reactant side. Okay, that's pretty cool. Now, if we take a look at our sulfates, well, sort of looking at the sulfates there, and I'm saying I've got 3 of this. I've got SO4 3 times. Okay, if I come over to this side here, and I put a 3 in front of this, that makes my sulfates balanced. Okay, now you can see the sodium listed first, but I didn't want it to list first. Now, we've got 3 of this molecule, and since there's already 2 sodiums in it 3 times, right? Just quickly writing that. Okay, that means that we've got 6 of these. Okay, so by putting the coefficient in 3 in front, our sodiums, happy joy, we're at 6, 6. So what's left? Well, what's left is take a look at chlorine. There's 3 here, you doubled the amount, so let's put a 6 here. Well, that's pretty awesome because now our chlorines are 6 and our sodiums, well, that balanced up nicely, 6. Pretty cool. So what we've done is we've figured out how this actually comes together. This, at the end, never had a number, but it's understood that there's got to be at least 1 aluminum sulfates at this dance, right, in these products. I didn't mess with any subscripts. I just made a mess with a whole bunch of writing. Okay, there are more of these than you could even believe. I remember when I was in high school getting sheet after sheet of these things. It's like, okay, is it ever going to stop? Well, let's go at a few of these, okay? And I promise to try to be brief. So let's take a look at what we got here. We want to leave hydrogen and oxygen to last, right? So let's take a look. Barium, well, there's 1 there and there's 1 there. So it's 1 to 1. I don't have anything I have to do. Okay, so here we do have to go after hydrogen and oxygen. So what do we got? When I look on this side, and if we do an accounting of hydrogen, we've got OH twice, right, as a polyatomic there, and we've got 2 here. So that is a total of 1, 2, 3, 4 hydrogens. Okay, if I'm going to deal with that, I have to do, getting ahead of myself. I'm going to have to put a 2 there. Okay, barium's fine. Hydrogen's a 4, 4. That accounts for 2 oxygens. And if you come over here, we take a look, there are 2 oxygens. So this puppy's balanced. Now you don't have to write these in, but just understand, this is what really goes on. This is what is going on in the reactants and products coming together. You could think of these as the, as the, 1 cup of this, 2 cups of this produces a cup of this and a cup of this, right? But all of your elements are accounted for. Okay, so what have we got next? Here's iron oxide combining with carbon. So we get iron and carbon monoxide. Well, that's kind of cool. So if you're going to chase this around a little bit, you'll say, well, it's Fe2O3, all right? So 2 irons, so I'll do this, 2 irons. Okay, that's fine. Now there's no hydrogens. Carbons appear balanced, right? So I'm not going to touch the carbons, but I do in the end have to go after the oxygens. There's 3 there, so I will write the coefficient 3. It's looking good, except we tripled our dose of carbon there. So coming over to the reactant side, I just put in a 3 there, and bada bing, 1 molecule of iron oxide. Now, of course, you're going to say, which kind of iron, right? If it's Fe2O3, and you kind of get used to this over time, this is 6 minus, right? So this, in order for this to be, to balance that, this would have to be iron 3. Okay, the 3 plus oxidation state. Just write in the 2 minuses, to be honest. There you go, like that. Okay, so what we've got a total of is a neutral amount. Perfect. So we're talking about iron 3. So 1 molecule of that, 3 molecules of carbon, you get 2 iron molecules, and you're left with 3 carbon monoxide molecules. Holy moly. Okay, speed this up. In the last example, or the next example here, I see a polyatomic here, and I see a polyatomic here, and that kind of grabs my attention because I can go after a polyatomic. So I'm going to go after nitrate. There happen to be 2 on this side, which is going to lead me to put 2 on this side. I get 2 potassiums out of that, so I'm going to balance that by putting 2 potassiums there. How's our lead look? Well, there's just 1 there, and there's 1 there. How do our iodines look? Awesome, because there's 2 there, and there's 2 there. So it's all accounted for. We're looking good. I'm going to, this example here, I'm going to come back to in a second because it's actually no, this is the final one. I'm not going to come back to it at all. I'm just going to do it. Sorry, I thought we had 2 different ones at the end. When you go to balance, some combustion reactions can be a major pain, okay? Because you go to balance this equation, you'll say, okay, I leave hydrogen and oxygen till last. Okay, hydrocarbons, you go after the carbon. Right. So because there's 2 there, I'm going to put a 2 here. Awesome. Hydrogen, I've got 6 there. Well, that's not a problem. I can put 3 there, and it's 6, 6. Products, reactants, it's looking good. And then you get to the end, and you say, holy moly, okay, wait a minute. I've got H2O 3 times, which means I've got an odd number here. And this is why you do oxygen last. You've got 3 there, and in CO2, you've got 2 there. So how many oxygens on this side? Well, your oxygen here, you've got a grand total of 4 Now you've got 7. And over here, your oxygen is 2. So don't panic, because you can go from the number 2 to the number 7, okay? And I say, it's just a little bit of rudimentary algebra. I'm just going to go over here. 2 times what gives me 7? I need a multiplier. Like, I've got to go from 2 to 7, right? How does that happen? It's a step 1 equation. Let's divide by 2. The number has to be 7 halves, which is like 3.5. You're like, 3.5, if I double that, I could get 7. Okay, that works. Now this is called fractional balancing, but you can't leave it that way. So if we take 7 halves of an oxygen, and just up at the top here, 7 halves times 2 equals 7. Remember how these cancel out? So this all is going to be well. You can turn 2 into 7. You just needed 3.5. So what do? You cannot have a 7 halves of an oxygen molecule. It just doesn't work. But the trick is this number on the bottom, right here. This denominator is 2. Whatever the denominator is what you multiply everything by. Why? Because that gets rid of the denominator. Remember how I told you in high school we didn't do fractional balancing? We had to figure these things out the hard way through sheer trial and error. What do you get here? The reason why you double everything is because this cancels with this, and you're just left with the number 7. Here's the final proportions. Okay, that's actually ethane right there. It's sort of like methane's bigger brother. You've got 7 oxygens. That leads you to 4 carbon dioxides, which gives you 6 waters. You notice that the bigger this gets, the more waste it produces. You should try doing this with octane, right? That's a pretty big chemical equation. But those are the proportions. 2 ethane molecules are combusted with 7 oxygen molecules. You get a whole bunch of carbon dioxide, 4 molecules of that, and you get 6 molecules of water. So in combustion reactions like that, you get a lot more products. Okay. Now, there is a lot for you to do here. There are a whole ton of these. What I want you to do is I want you to hit pause, okay? I could go over these equations ad nauseum, but it's very, very time consuming. And my daughter likes to point out, Dad, your videos are too long. And I'm like, I know, dear, and thanks for noticing. But seriously, hit pause. So I'm going to say pause, 1, 2. Okay, pause now. Don't cheat. All right, I'm going to assume you're back. Here are the answers to these devilish little questions. I'll write the ones in. You don't have to write the ones in. I'm just being thorough at this point, just so that you're expecting to see something there, so I'm going to put something there, right? This is how many molecules of these have come together. I wanted to give you a chance was to kind of go through a review, take some of these out for a spin. Now, you don't have to write down all the pictures or whatever. You could do this on an iPad, or you could just try some of the equations on paper. But I invite you to try it now. Figure out what you think the answers to the questions are. I'm going to pause. So I'll say pause 1, 2. You pause your video and give it a shot. Okay, so folks, pause 1, 2. Okay, so assuming we're back, hydrogen gas combining with nitrogen gas will give you a nitrogen trihydride. Okay, so that is the covalent naming, right? We don't say mononitrogen, we say nitrogen, and there's 3 hydrogens, nitrogen trihydride, but No one wants to say that all the time, so we gave it the name ammonia. Answer for this question's below. They're just showing you the coefficients, right? And if you look at your nitrogen molecules and your hydrogen molecules, how many do you expect to see at the end of the game? Well, law of conservation mass should tell you what you're going to get, okay? All right, so once again, pause, 1, 2, and we're back. You took these out for a ride. Let's see how you did. The answer to the first one, what's coefficient needed to be in front of oxygen in order to balance? You had to have 2 of them. Which of the following products would balance the reaction? Well, that's methane combusting, so carbon dioxide makes a lot of sense. Zinc, I'm going to tell you a secret. Whenever you put acid on a metal, you always get hydrogen gas. That is a reason, a very big reason, folks, why we don't use acids to clean our stoves. We use a base like sodium hydroxide because you don't get hydrogen gas, which is combustible. And in a stove, I think that would be a terrible idea, right? So what do you get? Where does the zinc go? Well, it becomes zinc sulfate. All right, another set of questions to try. All right, so pause, 1, 2. And we're back. What coefficient is needed in front of oxygen to make this work? You would need 5. You might notice that the bigger the hydrocarbon gets, the bigger the oxygen has to be. Well, because you're combusting a more complex material, there's more going on, so the amount of oxygen consumed goes up. And so does the carbon dioxide in the water. Which of the following equations is correctly balanced? It's that one. Chase your carbons first, then go after your hydrogens, and lastly your oxygens. Okay? Total number of, list the total number of each atom found below. And if you've been paying attention, right, you can do this trick. Like that, to help you count. So which thing in the table is correct? It's 3. Write the skeletal equation, right? That's an equation without any, coefficients being written in. So iron 3 bromide reacts with sodium hydroxide, and you get iron 3 hydroxide and sodium bromide. Holy moly, double switcheroo reaction. It would be that one. Then you'd have to go balance it. And that's great fun at parties. Another slide. Which of the following shows a balanced reaction of hydrogen and oxygen combined to produce water? And that is an interesting one. I'll speak a little bit to this one. Pause, 1, 2. Okay, and we're back. If you're like me, right, we take H2, and we take O2, because they float around like that naturally, right? You say, let's produce water. And then you say, you know what's annoying? 2 going to 1. Now, this is a trick. I like the balancing. If I could just reduce that, well, what's a half of 2? I have 1. Newsflash, you can't have a half an oxygen molecule. That doesn't work. What's the trick? You double everything, right? Like this. And really what it is it took 2 hydrogen molecules combining with 1 oxygen molecule, which floats around as O2, and that actually produces 4 H2Os. It's a little bit more complicated than a lot of people think. Now I've gone and done it, I've cheated. Well, no, I just did it symbolically. Now you can look at your diagram and say, which one is it? Okay, well, here we go. We had to have those kind of proportions. Here's your hydrogens, and here's your oxygens. Sweet. I personally find this a little bit quicker. This helps people sometimes who have a hard time visualizing the math, but when you start to get really large, complex molecules, it becomes a little, I wouldn't say annoying. It just you have to draw really big things, right? It's going to take you a long time to draw and color it in. All right, last page. I think this is the last page. What coefficient is needed for iodine in order to balance the equation? and the one below. So we're going to hit pause. 1, 2. Okay, and we're back. So what did you need? You needed to have 3 in front of that. Okay, so you're probably looking at the equation. You're like, oh, hold on. So they wanted to know this. Okay, well, yeah, 3, because this was 2, and now it's all balanced. It was one of those cases where you had to get the lowest common multiple of 3 and 2, 6, and that was how it worked out. So, bada boom. Which set of ordered coefficients balances the equation below? This one takes a little bit of work. Just write it in. Whew. Well, it's called chemistry for a reason. Ha, what's on the last page? If you were accounting for the weight, you took 32 grams of magnesium, and this is when you put a metal in basically zinc chloride is another ionic compound, and you're going to get a little switcheroo. What's going to happen is the magnesium and the zinc are going to change places. So if this was all accounted for, right, you had 32 grams of magnesium, 96 zinc chlorate, you're probably thinking, well, I've got my reactants, and I've got my products, right? And in terms of mass, you want to sort of produce a dividing line. 32, 96. And on this side, you've got 76 plus something. There's got to give me something. All right, pause with that predicate in mind. What's this got to be? So pause, 1, 2. Okay, we're back. You can't lose anything, folks. You can't lose the atoms, right? They have mass. So you got 128 grams accounted for. In the product side, they're saying, well, hey, you got 76. So what's the rest? Do the opposite of addition is subtraction. So if you've got to hit the magic number of 128, you got to take off the 76. Well, 2, I would estimate that should be 52. See if we were right. Good. Otherwise, the universe has gone crazy. Cats and dogs living in harmony. Okay, so one last one here. Again, you're combusting ethane, right? Which I always call methane's bigger brother. But then there's, if you go to a 3-carbon compound, you're up to propane, and then it just goes up from there. The more carbon you put in a molecule like this, right? The more hydrogen as well, the more powerful combustion reaction you get, which is why we run octane, which is an 8-carbon compound. But I digress. What's the answer? You would need, basically, the amount of carbon dioxide goes up like crazy. Like I said, the bigger the carbon compound, the greater the waste. Now, the very last one is like a word problem. It's magnesium chloride right? And sodium sulfide, like that. How do we know that it's that formula? Well, sulfide has a 2- charge. So there had to be 2 sodiums in that compound for it to be a balanced ionic compound, which is how it works. So if these two are going to come together, what coefficient are you going to need in order to balance the reaction? So let's take a look at that reaction. So here's the skeleton for it. MgCl2, sodium sulfide, produces magnesium sulfide and sodium chloride. You notice the magnesium is now dating the sulfide, and the sodium is now dating the chlorine. It's one of these things we call a double replacement reaction. So what did you need? Well, you needed a 2 there. Oops, went too fast. Now remember, they're saying what coefficient is needed in front of sodium chloride. So let's do this one completely before we sort of end the show. You're going to need 2 of these. Now let's make sure everything's balanced out. Do we have 2 sodiums on each side? Yes, we do. Right? They went after sodium, figured it out. Does that satisfy chlorines? Well, there's 2 there because of the coefficient, and there's 2 here. Looks good. Magnesium, well, looks like there's 1, and there's 1 there. And how about sulfide? There's 1 there, and there's 1 there. So these are 1s. Okay, folks, that is it. Thanks for listening to another edition, and keep at it. Balancing equations can be a lot of work. It was a lot of work for me in high school because they never taught me fractional balancing. But I got over it and learned it. Passed it on to you. Ciao.